Hello and welcome to Computational Techniques web course. We are now on module 6. In module 6 we are going to discuss differentiation and integration, numerical differentiation and integration specifically. So, given a function y equal to f of x, sometimes we may not have function y equal to f of x, but just data points xi or yi, or methods to just generate this data points xi comma yi. Okay. So, no matter how we do that, let us assume that we have some kind of a curve y equal to f of x and we are interested in obtaining differentiating and obtaining the value dy by dx. Okay. What it means geometrically is that differentiation is nothing but obtaining slope of the tangent segment to the curve at the desired point. Okay. So, this is the curve f of x and the slope of the tangent at f of x is just the numerical derivative. Okay. But when if f of x is not available, or if it is very difficult to differentiate this f of x analytically, we can resort to numerical techniques, and numerical techniques, this is the numerical approximation for the f of x. dy by dx definition is nothing but limit as delta x tends to 0 delta y divided by delta x, which we can approximately write as equal to y of I plus 1 minus yi divided by x I plus 1 minus xi. This is delta x and the the numerator is delta y. Okay. So, as we bring xi plus 1 closer and closer to xi, we will start approaching the numerical derivative, will start approaching the analytical or the actual derivative dy by dx. We cannot take xi plus 1 very close to xi, because then round of errors will start dominating. This particular method is just a first order method to find a numerical differentiation. We will use Taylor series expansion in order to get higher order and more accurate methods for numerical differentiation. So, that is the overall general setup, and if we compare from the slope of the tangent, the actual tangent to this, with the numerical approximation of the tangent. So, in this particular figure, when we look at that, as you can compare the two red lines, the slope is different in those two cases. Okay. So, what is happening is that the numerical approximation is not going to be an exact representation of the differentiation, but it is going to be an approximate representation of the differentiation. Let us now talk about integration. In integration, again we are given the function y equal to f of x or some data xi yi between the values a and b, and we are interested in finding out the integral from a to b of fx dx. Okay. Integration is nothing but obtaining the area. This is the same curve. Integration is obtaining the area under that curve between points x equal to a to point x equal to b. This shaded area that we see over here is the integral from a to b fx dx. Okay. And geometrically what it means is we will draw the various grid points as shown over here, and the integration is nothing but the summation of the total number of rectangles that we have over here. Clearly, if we take smaller and smaller gaps in this particular gridding, that means if we grid this in a much more finer mesh, we will get more accurate value of the integral when we do this numerical integration, and those concepts are something that we will try to understand when we do numerical integration, when we do numerical integration using various methods for integration. Okay. Now, the next question of course that comes to mind is, where is differentiation, numerical differentiation and numerical integration going to be used, and the application of numerical differentiation is, one application is in Newton-Raphson's method. What if f of x is obtained such that it is very difficult to find f dash of x? In such cases, in Newton-Raphson's method we will use numerical differentiation. If f dash is not available, we can then use a numerical value of f dash. Remember, the numerical differentiation of f dash was xi plus 1 minus xi. We will write xi plus 1 as nothing but xi plus delta. So, this is going to be f of xi plus delta minus f of xi divided by xi plus delta minus xi. So the denominator for f dash is nothing but delta, because f dash is itself is in the denominator, the delta becomes a numerator in this Newton-Raphson scheme. So the Newton-Raphson scheme, when the analytical derivative f dash of x is not available, becomes xi minus delta of f divided by f of x minus x plus delta minus f of x. That is the value that we will get for the Newton-Raphson's method. Couple of examples of numerical integration is, in order to calculate the mean, in the mean that we obtain was nothing but summation of x divided by the number of data points, but if we want to calculate the mean of an independent variable related to the dependent variable, the mean of the dependent variable f of x related to the independent variable x, the mean is calculated using an integral of this sort. It is 1 divided by b minus a integral from a to b fx dx. So this is one place where integration will be required. Another example where integration is required is the mass flux calculation. So let us say we have a tube through which some kind of reactors are some kind of fluid is flowing. In that particular case, the mass flux of any species in the fluid is going to be represented as the area integral with respect to x and y coordinates of the overall flow flux, which is rho multiplied by u multiplied by wk. Wk is nothing but the mass fraction of the species k in this particular system. Another example is to calculate the net heat loss happening through this particular surface, and the net heat loss through the surface is the surface integral of flux multiplied by the surface, the differential surface ds. We will integrate it over entire surface S. So that is going to be the flux that exits from any infinite similar area in this overall body. Okay, this is how we will calculate the flux. Another example of integration is the design equation of plug flow reactor. So if you have done your reaction engineering course, or already you will recognize this design equation for plug flow reactor, and you will also be able to recognize this Leuwenspiel plots in order to find out the volume of the PFR and volume of CSTRs that we are going to use. In this particular case, what we do is we plot 1 divided by RA as the y axis and the conversion x on the x axis, and this is the curve that we get. The area under the curve is nothing but the volume of the CSTR that is going to be required, V by F for that CSTR. So this is the curve we get for a first order reaction kinetics, for example, and this is the curve that we will get for biological reactors. Okay. So what are we going to cover in this module? The overview that we are going to cover in this module, we will first cover numerical differentiation, perhaps in about 1.5 to 2 lectures, and then we will cover numerical integration, which will be covered perhaps in about 3.5 to 4 lectures. In numerical differentiation, we will look at forward, backward and central difference schemes, and then we will look at the multi-point method, and then we will do the error analysis. As I had mentioned in the passing previously, what we find is that as we take xi plus 1 closer and closer to xi in numerical differentiation scheme, we find the error reducing, but we cannot bring xi plus 1 too close to xi, because then although the truncation error reduces, the round of error is going to increase. That is what we will cover overall in the numerical differentiation. In numerical integration, we will cover various methods to do numerical integration, specifically the trapezoidal rule, Simpson's 1/3 and 3/8 rules. Then we will talk about Newton's extrapolation, how we can use, the Richardson's extrapolation, how we can use Richardson's extrapolation to improve Simpson's 1/3, 3/8 rule or trapezoidal rule, and finally we will talk about Gauss quadrature method. The first two methods come under the more general title of Newton-Cotes formulae, whereas a Gauss quadrature method is kind of an open method. We will talk of all these methods in the numerical differentiation and integration that we will cover in the current module. Start off with numerical differentiation over here. We have So at any point xi we want to find dy by dx, say y equal to some function f of x, at x equal to some xi we want to compute dy by dx. That is the question that we are trying to ask ourselves. Dy by dx is nothing but the slope of the curve fx versus x at value xi. Okay. So let us make the curve in this form. Let us consider this as point I, let us consider this as point I plus 1, and let this be the point I minus 1. Okay. So we are interested in finding out the slope of this particular curve. The slope of this curve the slope of the tangent to this curve at point I. So I will just draw the tangent segment over here. So the yellow represents the true derivative dy by dx. Okay. We are plotting x versus y, x as the abscissa, y as the ordinate. Okay. So at x equal to xi we can write dy by dx at I as approximately equal to y I plus 1 minus yi divided by x I plus 1 minus xi. Okay. This is the forward difference form. Okay. And this can be represented as a line, the slope of the line joining the points xi yi with the point xi plus 1 yi plus 1. Okay. So the red line that I am showing over here is the forward difference approximation. Okay. And alternatively we can write dy by dx at I as y of I minus y of I minus 1 divided by xi minus xi minus 1. Okay. Just the way we had written it in this form, we can write it alternatively in this form. This becomes our central difference formula. Okay. And the central difference formula in this particular case is going to be nothing but the line joining xi minus 1 yi minus 1 to xi yi. Okay. So I will have this joined with a dotted line. Okay. And this I will call as backward difference. Okay. And the third possibility, again a third possibility that you would have considered previously is what is known as the central differences, and in the central differences we will have dy by dx written approximately equal to y I plus 1 minus y I minus 1 divided by x I plus 1 minus x I minus 1. Okay. What that is it is nothing but the slope of the curve that joins the point x I minus 1 y I minus 1 with the point x I plus 1 y I plus 1. Okay. So it is slope of this particular dotted curve. Okay, I am not drawn it too well. Okay. So I will just join it with another yellow dotted line over here. Okay. And this is the central difference. Okay. So the yellow solid line is the true dy by dx, the true derivative of the function y equal to f of x with respect to x at point I. The red solid line is the forward difference approximation. We can clearly see over here that the forward difference approximation of the dy by dx is, there is a fair amount of error associated with it. Likewise, there is a backward difference approximation shown by this particular dashed line. There is a fair amount of error even in the backward difference approximation for this particular system. The slope of the dashed line in the central difference approximation turns out to be much closer to the slope dy by dx compared to either of those two red line segments that I have shown. Okay. So that is the whole idea behind using some of the forward and backward and central differences in order to get the numerical derivatives or the approximations of the numerical derivatives given a function, either given a functional form f of x, or there has to be some mechanism to generate the values of y given the values of x using some kind of a function y equal to f of x. Okay. So let us analyze what are the various truncation errors associated with these numerical derivatives. Truncation errors in numerical differentiation. Y of I plus 1 is nothing but f of x of I plus 1. Okay. So f of x of I plus 1, we will write that approximately equal to, we will take a Taylor series expansion around xi. Okay. So that is approximately equal to f of xi plus xi minus 1, we will write that as delta x f dash of xi plus delta x squared by 2 factorial f double dash of xi plus dot dot dot. Okay. That is what our y I plus 1 is going to be. Okay. So likewise we can write y I minus 1 also. So I'll just write y I plus 1 again in the shorthand notation. Y I plus 1 is equal to y I plus delta x multiplied by y dash I plus delta x squared by 2 factorial multiplied by y double dash I plus delta x cube by 3 factorial multiplied by in this particular case we will write f triple dash of zeta, where zeta is some point lying between xi and xi plus 1. Okay. We get this using the mean value theorem, we are able to obtain this. Okay. Likewise, we will be able to write as y I minus 1 as y I minus delta x times y dash I plus delta x squared by 2 factorial y double dash I minus delta x cubed by 3 factorial f triple dash of zeta. Okay. Now what we will do is subtract these two equations. If we subtract these two equations, okay, we will get y I plus 1 minus y I minus 1 is going to be equal to yi and yi will get cancelled, we will get x delta x plus delta x multiplied by y dash. So it is going to be 2 times delta x multiplied by yi dash. These terms are again going to get cancelled and this will be plus 2 times delta x cube by 3 factorial multiplied by f triple dash of zeta. Okay. We divide throughout by 2 delta x and we take this particular term on to the left hand side, rearranging we will get the final result, that is yi dash is going to be equal to yi plus 1 minus yi minus 1 divided by 2 delta x. Okay, we have divided throughout, we have taken this 2 delta x and divided throughout. Okay, so this 2 and this 2 will get cancelled, instead of delta x cubed we will have delta x squared, and because we have taken this term to the other side it will get a negative sign. Okay, so we will have this as minus delta x squared by 3 factorial f triple dash of zeta. Okay. This part is the central difference approximation. Okay, and this represents the truncation error. Okay, and in the central difference approximation the truncation error is proportional to delta x squared. Okay, so that means if you make the delta x 1/10, the truncation error is going to reduce by 1/100th. If you double the delta x, you are going to make the error, truncation error in dy by dx 4 times greater. Okay, so that is what this particular thing means. So in conclusion, yi dash, that is the first derivative of yi using the central difference approximation, is yi plus 1 minus yi divided by 2 twice delta x, and the truncation error in the central difference is of the order of delta x squared. Okay. Now let us look at the forward difference approximation. In forward difference approximation, let us go back to what we had written over here. Okay, what we will do is we will take yi on to the left hand side and divide throughout by delta x. When we do that, what we will get is yi plus 1 minus yi divided by delta x is going to be equal to yi dash plus delta x by 2 factorial f double dash of I plus bunch of other terms. This is the leading term over here, based on another mean, again applying mean value theorem. This term will become delta x divided by 2 factorial f double dash of some value, some other value zeta. We will just call it zeta bar because this zeta is different, may be different from this particular zeta. Okay. So in this particular case, this becomes our forward difference approximation, and this represents the truncation error. Okay, and truncation error in forward difference approximation is proportional to delta x to the power 1, or it is proportional to delta x. Okay, and going back to the geometric interpretation that we had of Newton's forward difference and backward difference and central difference formulae, this is what we had seen with forward, backward and central difference, forward, backward and central difference, and what we had stated at that time is, from this particular cartoon it looks as if central difference approximation does a better job of approximating the actual derivative numerically compared to the forward difference and the backward difference. The derivation that we have obtained using the Taylor series approximation over here verifies that particular geometric intuition or the geometric claim that we had made in the previous previous part of this lecture, that truncation error reduces as delta x squared for central difference, whereas it reduces as delta x to the power 1 for the forward difference approximation. Okay. So at this stage we will end the module 1 sorry lecture 1 of module 6. What we have covered so far is forward and central difference approximation for the first derivative of any function f of x. What we will cover in the next lecture is to look at the higher derivatives, that is f double dash, f triple dash of x, so on and so forth, as well as higher order accurate formulae. We will use another different method called the method of undetermined coefficients in order to determine the higher order formulae also, and finally we will finish off with talking about truncation versus round of errors. Okay, so what we have seen so far is how to get the first derivative of that is dy by dx given some kind of a function f of x, either a function f of x or discrete value of f of x at certain given points of x. We have looked at how we will get the first differential with that. Now let us look at this, how to get the second derivative from this. So what we want to get actually is d squared y by dx squared at x equal to xi. Okay, so this is what we are interested in getting, where y equal to f of x. So that's the overall function that we have. As we had done before, what I will do is I will write down the same expressions all over again, is f of x I plus 1 is f of xi plus delta x times f dash of xi plus delta x squared times f double dash of xi plus delta x cube times f triple dash of zeta, and I forgot divided by 2 factorial and divided by 3 factorial over here. Okay, so this is the overall expression that we get on expanding f of xi plus 1. Likewise we will expand f of xi minus 1, and that is going to be f of xi minus delta x times f dash of xi plus delta x squared by 2 factorial f double dash of xi plus minus delta x cube by 3 factorial f triple dash of xi plus dot dot dot. In fact, I will change this to f triple dash of xi plus dot dot dot. Okay. Now I will add these two equations. So when I add these two equations, we will get f of xi plus 1 plus f of xi minus 1 is going to be equal to twice f of xi. This term and this term will get cancelled, this term will be retained, so it is 2 times delta x squared multiplied by f double dash divided by 2. So we will have plus delta x squared f double dash of xi. This term and this term will get cancelled, the leading term that will remain is going to be 2 times delta x to the power 4 divided by 4 factorial f 4 dashes of xi plus dot dot dot. Okay, so this is the leading error term that that we have, and for this part of the equation we will apply the overall mean value theorem, and we will convert from xi to zeta, where zeta is going to be any point that lies between xi minus 1 and xi plus 1. Okay. So what we'll do is we'll take this twice f of xi on to all the terms rather except delta square f double dash, all other terms will take on to the left hand side and divide throughout by delta x squared. So when we do that, we will have f of xi plus 1 plus f of xi minus 1 minus 2 times f of xi, okay, minus 4 factorial is going to be 4 multiplied by 3 multiplied by 2 multiplied by 1, that guy divided by 2 is going to be 4 multiplied by 3, which is essentially 12. So minus delta x to the power 4 by 12 f 1 2 3 4 of zeta is going to be equal to delta x square f double dash of xi, okay, and we divide delta x square throughout and we will get our final result is f double dash of xi is going to be equal to f of xi plus 1 minus twice f of xi plus f of xi minus 1 divided by delta x squared, okay. So if you look at this particular expression, it's f of xi plus 1 plus f of xi minus 1 minus twice f of xi divided by delta x squared, and this is the residual term which would be delta x squared by 12 multiplied by f 4 dash of zeta. So minus delta x squared by 12 f 1 2 3 4 of zeta, okay. So this is the central difference formula, okay, and this is the error in the numerical derivative, okay. So what we have seen so far is that for the central difference formula, either whether we are going to use the central difference formula for finding f double dash or we are going to use the central difference formula for finding f dash, we observed that the error is proportional to delta x squared, okay. So as we reduce our delta x to smaller and smaller values, the error, the truncation error in fact reduces as the delta x is reduced, okay. And in the forward difference method or the backward difference method for getting f dash, that reduction is directly proportional to delta x, whereas in the central difference method it is proportional to delta x squared. As a result of this, the central difference methods are going to be more accurate than the forward or the backward difference methods, okay. So in order to summarize the other f dash x values that we had gotten, f dash of xi was equal to f of xi minus f of xi minus 1 divided by delta x, plus error was of the order of delta x. F dash of xi that we wrote as the central difference formula was f of xi plus 1 minus f of xi minus 1 divided by twice delta x plus order of delta x squared, okay. And like this we could also write the forward difference method where f dash of xi was equal to f of xi plus 1 minus f of xi divided by delta x, okay. So these are the derivations based on the Taylor series expansion. What I will do next is do one more derivation again of the same formula. The purpose of doing this derivation is to introduce a new method called method of undetermined coefficients. We will use this method because this method is more general and you can apply it to get higher order formulae, more accurate formulae, so on and so forth, okay. So this method is called method of undetermined coefficients. Okay. So we will go back to what we had written as our Taylor series expansions. We had written our Taylor series expansions for fxi plus 1, we had written our Taylor series expansion of for fxi minus 1, and then we could pick and choose which data points do we want to use in order to get the first differential or the second differential or higher order differentials of f. Okay. So I will demonstrate that method. Again we will try to find f dash of x. So I will write our f dash of x as some a1 multiplied by f of x I minus 1 plus a2 multiplied by f of x I plus a3 multiplied by f of x I plus 1. Okay. So our undetermined coefficients are a1, a2 and a3. What we are trying to do is we are trying to get a 3-point difference formula for the first derivative f dash of x at the at x equal to xi. So we are trying to get a 3-point difference formula. Why 3-point difference formula? Because we are going to use point xi minus 1, xi and xi plus 1 in order to get to derive that particular formula. Okay. So what is the 3-point difference formula for f dash of xi? 3-point difference formula for f dash of xi is nothing but the central difference. So what we expect is really our a1 over here, if we compare it to this particular equation, what we expect our a1 to be is minus 1 by 2 delta x, we expect our a2 to be equal to 0 and we expect our a3 over here to be equal to 1 plus 1 divided by 2 delta x. So we have 3 undetermined coefficients, so we require 3 equations, 3 linearly independent equations in order to obtain unique values of a1, a2 and a3. Okay. So we will substitute the Taylor series expansion over here, Taylor series expansion over here and the Taylor series expansion over here. So we can write down f dash of xi is going to be equal to a1 times f of xi minus 1, which is f of xi plus delta x, I am sorry not plus, it should be minus delta times f dash of xi plus delta x square by 2 factorial f double dash of xi plus delta x cube by 3 or sorry again minus delta x cube by 3 factorial f triple dash of xi plus dot 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 plus a2 times f of xi plus a3 times f of xi plus delta x f dash, I will just use shorthand f dash of I plus delta x squared by 2 factorial f double dash of I plus delta x cube by 3 factorial f triple dash of I. Okay. Now we will collect the terms in f, f dash, f double dash, f triple dash and so on and so forth. So what we will get is f of xi multiplied by a1 plus a2 plus a3. So fi multiplied by a1 plus a2 plus a3 plus f dash of xi multiplied by a1 multiplied by minus delta x, a2 multiplied by 0 because there is no f dash term over here, and a3 multiplied by plus delta x. Okay, plus f double dash of I, and the terms in f double dash of I are going to be a1 multiplied by delta x square by 2. So a1 delta x squared by 2 plus a2 multiplied by 0 plus a3 multiplied by delta x square by 2. Okay, and then we will have other terms which is f triple dash of I, and there we will have minus a1 delta x cube by 6 plus a3 delta x cube by 6 and so on and so forth, plus dot dot dot. Okay. So now what we have on the right hand side we have an f dash of I term, on the left hand side we have terms in f dash fi, f dash of I, f double dash of I, so on and so forth. Okay. So what we will do is we will identify each individual term with different colors, f dash of I, and we have this as f dash of I. So what this means is that the coefficient of f dash of I is nothing but 1 multiplied by f dash of I, and that coefficient should be equal to this particular guy over here. Okay. So we will equate that, we will equate the red box term in this part on the right hand side with the red number over here. All the other terms appearing should be equal to 0. Keep in mind that because we do not know a1, a2 and a3, we require 3 equations. So the first equation is going to be a1 plus a2 plus a3 equal to 0. The second equation is going to be minus a1 delta x plus a3 delta x equal to 1, minus a1 plus a3 multiplied by delta x is going to be equal to 1, and the third equation is going to be a1 delta x squared by 2 plus a3 delta x squared by 2 equal to 0. So a1 plus a3 multiplied by delta x squared by 2 equal to 0. That is going to be our third equation. Okay. So based on this we will write a3 equal to minus a1 based on this equation, substitute it over here. So we will have 2a3 equal to 2a3 delta x is going to be equal to 1, or a3 is going to be equal to 1 by 2 delta x. Okay. Based on this equation we will have a1 is going to be equal to minus 1 by 2 delta x, and a2 based on this particular equation is going to be minus of a1 plus a3, which will be 0 because a1 is minus 1 by 2 delta x and a3 is equal to 1 by 2 delta x. Okay. So the value of a1 is this, value of a2 is 0, value of a3 is 1 by 2 delta x. Okay. So that is the overall equation that we get using the method of undetermined coefficient. So we substitute a1 over here, a2 over here, a3 over here, and this is the result that we will get. Essentially it is going to be the central difference formula. Now the question is, what about the error term? Okay. And the error term, to figure out, what we have to do is substitute the value of a1, a2 and a3 in this particular term, the terms that we have neglected. Keep in mind that this has become 0, this term has become 0, this term has become 1. All the above, all these terms are actually non-zero, but we are neglecting it. Okay. So error is going to be equal to minus a1 by 6 plus a3 by 6 multiplied by delta x cubed multiplied by f triple dash of xi, plus we have other terms as well. Now if we substitute a1 and a3 in this particular equation and this term turns out to be 0, then we will have to look at the next term. If this term does not turn out to be 0, this becomes the leading error term and we stop our error analysis at this point. Okay. So let us substitute A1 equal to minus 1 by 2 delta x and A3 equal to 1 by 2 delta x. So error is going to be equal to minus it's going to be equal to minus 1 by 2 delta x multiplied by minus 1 by 6. So it's going to be 1 by 12 delta x plus 1 by 12 delta x multiplied by delta x cube f triple dash plus dot dot dot, and this becomes equal to 1 by 6 multiplied by delta x squared. This delta x and one of the delta x's over here will get cancelled, multiplied by f triple dash. Okay. As a result of this, the error that we write over here is going to be equal to 1 by 6 delta x cube f triple dash of xi. Okay. So this is the error in central difference of f central difference f dash of xi. Okay. So this is the overall derivation using the method of undetermined coefficients. Now sometimes what we need is we need either a higher order method using forward difference formula or higher order method using backward difference formula, so on and so forth. So what I am going to do is I am going to show you one more result using what is known as 3-point difference formulae. So okay, we are going to use the method of undetermined coefficients to get 3-point forward difference formula for f dash of xi. We will write f dash of xi equal to a1 f of xi plus a2 f of xi plus 1 plus a3 f of xi plus 2. Why is it called the 3-point forward difference formula? Is because in order to get the derivative at this point xi, we are going to use the values at xi plus 1 and xi plus 2. Okay. So we are using, for getting the derivative at this point, we are using this point and this point. So we are using 3 points ahead or forward of xi, that is why it is called a 3-point forward difference formula for f dash of xi. Okay. So we substitute f of xi plus 1 and f of xi plus 2 in this particular equation. So we will have a1 fi plus a2 multiplied by fi plus delta x f dash of I plus delta x squared f double dash of I by 2 factorial plus delta x cube divided by 3 factorial f triple dash of xi plus dot 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 plus a3 multiplied by fi plus, now we in this particular case x, the difference between xi plus 1 and the difference between xi and xi plus 2 is 2 times delta x. So it will be 2 times delta x multiplied by f dash of I plus 2 delta x whole squared divided by 2 factorial f double dash of I plus 2 times delta x the whole cube by 3 factorial f triple dash of I plus dot dot dot. Okay. Now we collect the terms in fi, f dash I, f double dash I, so on and so forth together. So we will write f dash of xi is going to be equal to f of xi multiplied by a1 plus a2 plus a3 plus f dash of xi multiplied by a2 times delta x plus 2 a3 times delta x okay plus f double dash of xi multiplied by a2 delta x squared by 2 factorial. I will take delta x squared by 2 factorial outside the bracket okay. So we will have a2 multiplied by delta x square f double dash by 2 factorial, so that multiplied by a2 plus a3 multiplied by 4 delta x squared by 2 factorial multiplied by f double dash. So 4a3 multiplied by delta x square by 2 factorial plus 4a3 is what we get for f double dash plus terms in f triple dash okay. So our three equations are going to be a1 plus a2 plus a3 equal to 0, a2 delta x plus a2 2a3 delta x equal to 1 and a2 plus 4a3 equal to 0 okay. So I will write down the three equations over here. A1 plus a2 plus a3 equal to 0, a2 plus 2a3 times delta x equal to 1 and a2 plus 4a3 times delta x squared by 2 factorial equal to 0. This particular term gets cancelled, a2 equal to minus 4a3, substitute this over here, we will get minus 4a3 plus 2a3 equal to 1 by delta x. So a3 is going to be equal to minus 1 by 2 delta x okay. A2 is going to be equal to 4 by 2 delta x okay, and a1 is negative of a2 plus a3, which is going to be equal to negative of 1 by 2 delta x 4 minus 1 okay, which is equal to minus 3 by 2 delta x okay. So we substitute these values in this particular expression and the result that we will get for a 3-point forward difference formula is f dash of xi is going to be approximately equal to minus 3 by 2 delta x f of xi okay, minus 3 by 2 delta x f of xi plus 2 divided by delta x f of xi plus 1 minus 1 by 2 delta x f of xi plus 2 okay, and this is our 3-point forward difference formula. And if we substitute the value of a1, a2 and a3 in the f triple dash term, we will realize that the error of the leading term is of the order of delta x squared. So a 3-point forward difference formula has an error which without derivation I am just stating error is proportional to delta x squared okay. So we now have a forward difference formula which is more accurate than our traditional 2-point forward difference formula for f dash xi. Okay, this we have obtained using the method of undetermined coefficients. To summarize what we have done in this particular lecture until now is, we started off with an introduction to numerical differentiation and integration. We motivated the numerical differentiation and integration part, saying where exactly numerical differentiation and integration will be useful, and then we started covering some of the methods for getting the numerical differentiation using the forward difference method, backward difference method, central difference method for getting f dash of x. Then we talked about the method of undetermined coefficients, where we write our f dash of x as a linear function of f computed at various different points, and then we used a method in order to compute this particular or these particular coefficients. And finally we talked about higher order formulae, for example 3-point forward difference formula, in order to get f dash of xi. Okay, so that is essentially what we have covered in this particular lecture. In the next lecture I will briefly recap all these formulae, and then I will go on to taking a couple of numerical examples to show what we have derived in these particular equations. Okay, thank you.